Hello, my name is Tony Lentz with FCT Assembly. This paper is titled Fill the Void 5, Mitigation of Voiding for Bottom Terminated Components. It was originally presented at IPC Apex Expo 2020. My co-author on this work is Greg Smith with Blue Ring Stencils, who was not able to make this video recording with me. First, we'll talk a little bit about voiding. What is all the fuss about? Why are we all discussing voiding and writing papers on voiding in solder joints? Why is it important to us? And we'll talk a little bit about the causes of voiding, what are the potential factors that can contribute to that, and what did we specifically test in this work. Then we'll go into some detail on the methodology or the way we set up the experiment. Then I have lots of results to share with you. The results are broken out by stencil thickness, area of coverage, by component size, component type, and by the input-output pad toe adder, or the stencil design that we used to make these experiments. And then at the end, I'll have some conclusions, and we'll give recommendations on how to mitigate voiding on your own circuit boards. So when we talk about voiding, what is all the fuss about? So voids are very large, or there's a high void area, or there's a lot of voids concentrated on a plane in the solder joint, like between the component and the solder joint or at the board pad interface, then that can lead to mechanical failure or cracking in the solder joint, like what is shown in this BGA cross-sectional picture on the left. You can see a very large void in the center of that BGA sphere, and that led to cracking in the solder joint. Voids can also lead to overheating failure of components. This is especially a problem for bottom terminated components that are using a central thermal pad to transfer heat out of the component. If the void area is too high, then you can get that acts like an insulator essentially, and it can resist the heat transfer out of that component. LED components are really susceptible to this. They generate a lot of heat, and they use solder joints in order to move some of that heat away. And so if the solder joints have too high of voiding, then that component could burn out prematurely. Then the last problem that I've heard about with voiding is electrical signal degradation or noise in the circuit. And that's especially a problem for RF circuit designs. The bottom line is voids are hard to rework. Once a void exists in a solder joint, the only thing you can really do is try to melt that solder joint and resolder it, but it's very difficult to totally eliminate voids that way. I've seen voids reappear under those conditions. So the best option is to try to limit the amount of voiding that's going to form, reduce the void area through mitigation factors up front. So here are some of the causes that can contribute to voiding. This is a pretty small fishbone diagram with cause and effect of different aspects of the SMT process. In terms of print or dispense, the volume of solder paste that's printed, or more specifically the stencil design of both the thermal pad and the perimeter pads, is important in terms of voiding for QFN type components. Reflow profile certainly has an effect on voiding. Adjusting the reflow profile and tuning it to make it work with the solder paste and the circuit board can have some impact. It can minimize voiding to a certain extent. And the solder paste itself certainly plays a role in voiding. Those are the three major areas we're studying in this particular work. In prior work, we've studied several of these other factors and in relation to voiding and how they impact voiding. So what can we change in our process in order to get rid of voiding? The stuff that's easy to change is shown on the left. The stuff that's harder to change is shown on the right. The easy to change stuff would include your solder paste. You could quickly get a sample of solder paste from another supplier within a few days, maybe a week, put it on the process. Some solder pastes have lower potential for voiding than others, so that change alone might help reduce voiding. You can certainly change the stencil design pretty quickly. You could talk to your stencil supplier, get a modified design made and shipped, and you could have it in your process the next day, and that may have an impact on voiding. And changing the reflow profile obviously is fairly easy too. Reflow profile modifications can be done within an hour or two, and that may have an impact on voiding. The stuff that's harder to change but also has a big effect on voiding is the board design itself and the components that you use. For example, using a bottom terminated component like a QFN rather than a leaded component like a QFP is going to lend itself to higher voiding levels. Voids tend to congregate in that solder joint, and if it's a gas bubble type void, it's going to rise up to that flat bottom of a bottom terminated component and then not be able to move much. It's not going to migrate. Whereas with a component that has a higher standoff, the solder joints don't have a hard top on them, and so the voids can make it their way to the top surface of that solder joint and then burst out like a bubble, and then the solder joint can collapse and coalesce and have much lower voiding because of that. V and pad designs also contribute to voiding. There's a lot of things with board design and components that can create situations where voiding is prevalent. The reflow equipment that you use itself can have a large impact on voiding. If you can use vacuum in your reflow process, that's one sure way of reducing voiding regardless of all these other factors. But it's not easy to just go buy a piece of reflow equipment with vacuum and throw it into your process. But if you are looking to buy new reflow equipment, I would recommend considering something with vacuum or something with ultrasonic agitation, something that has some technology in it to help reduce voiding potential. And then the surface finish of the circuit board itself, it's kind of part of board design and components. I separated it out here because it does have an impact on voiding. And recently I've written a couple of papers studying that itself. I looked at different surface finishes and what impact they had on solder paste performance, just generally speaking. But one of the things I looked at specifically was voiding potential based on surface finish. And there's a big difference from one surface finish to the next. So if you have the ability to change surface finish, you should certainly consider that. If you don't, I understand sometimes you're given surface finishes that you don't have any control over which one is given to you, and you just have to make it work. The papers that I was talking about in terms of surface finish discuss that a little bit and give recommendations on how to deal with different surface finishes. So here's the methodology or how we set up our experiment. On the left is the circuit board design that we used, and on the right is the stencil design that went along with that. We're basically using the lower half of this circuit board, the QFN 10s, which are circled, and the QFN 7s and the QFN 4s. Those are 10 millimeter, 7 millimeter, and 4 millimeter body components. We are not using the columns in the center here. Those are QFN 9 millimeters. And then the circuit board laminate material was standard FR4, 0.062 inches thick with 1 ounce copper. It's an printed and etched type circuit design with standard semi-matte green solder mask and an ENIG surface finish. And then the stencil design that we used on the right was varied pretty widely for each one of these components. So each one of these components has 2 columns. So the QFN 10 component, for example, has a 70% area of coverage in the first column, then 60% area of coverage in the second column. And then the rows give different perimeter lengths on the I/O pads. And so the first row is 1-to-1 with the copper. So the printed solder paste brick is the same size as the I/O pad on the copper. The second row has +5 mils added onto the toe. The third row has 10 mils added onto the toe of that solder paste print, and the fourth row at the bottom here has 20 mils added onto the toe of that print. And so the theory here is by adding solder paste onto the toe, when those perimeter pads reflow, the solder paste becomes a taller bump. If you're adding length onto the toe, it pulls back, makes a taller bump, so it lifts the QFN component a little higher, allowing some room for gases to escape from that center thermal pad solder joint. So we did that variation on the stencil design coupled with different component sizes and also coupled with these different areas of coverage on the thermal pad. In prior work, we've seen that different areas of coverage on the thermal pad have a big impact on voiding behavior. Here's a full breakdown on the stencil design in case you're interested. We've got 3 components, QFN 10, QFN 7, QFN 4 on the left, and then the thermal paste areas, the number of panes we use, the web width, the brick size itself. Then on the perimeter pads are shown on the right side of this table. All the perimeter pad widths are shown, and then after that it's the length for the 1-to-1 pad, the length +5 mils, +10 mils, and +20 mils. So that's a breakdown on how we design these stencils. And if you want more detail on that, we can certainly get you in touch with Greg Smith, who designed the stencil. Two stencil thicknesses were made. We made a 4 mil thick and a 5 mil thick stencil with the same exact designs. So we varied the volume again by 20% roughly by changing the stencil thickness from 4 to 5 mils. Well, from 5 to 4. 5 was the standard stencil thickness, reduced it to 4. And so we have a combination of varying the area of coverage on the thermal pad, the stencil thickness, and then the perimeter or IO pad lengths of print. We tested 5 different reflow profiles with this. The first reflow profile is a linear ramp to spike, and you can see the measured parameters shown here. The slope, the soak time, the reflow time, the peak temp, and the total length of the profile. We made a short version of that linear ramp, and the short version is about 3.9 minutes long versus about 4.5 minutes long for the linear ramp to spike. So we took about 30 seconds off the profile length. Then we made that same short profile, but we added a soak to it. So we added about 30 seconds in that soak zone of 150 to 200 C, and the overall length was increased by that amount of time. And then we made a long version of the linear ramp profile. So this is a linear ramp to peak, just longer. So the length of the profile on the very right is about 5.5 minutes versus 4.5 minutes. So we bumped it up by a full minute. And then we took that long profile and added a soak to it. So we added again about 30 seconds in the soak temperature range. And then the length was increased roughly by that same 30 seconds. After testing all 5 of these profiles in preliminary experiments, we measured voiding on the circuit boards, and we found that overall for this design and for the solder paste that we chose, this linear ramp to spike profile gave the lowest overall voiding. So it's highlighted in green. And that's the profile that we used to continue this work for all the other experiments. Here's a plot of that linear ramp to peak profile that we chose. Again, that was the lowest overall voiding with the solder paste that we used. Now, if you use a different solder paste, I would recommend doing something similar, testing several different profiles based on your solder paste supplier's recommendations. One of those profiles is probably going to give you lower voiding than the others. Or in some cases, maybe 2 or 3 profiles all give similar voiding results, and maybe 1 or 2 give higher voiding results. It just depends on the solder paste and the circuit board design. The statistics that we're going to show to talk about voiding are shown here. We're going to use box plot diagrams. So the way this works is on the y-axis we have void area percentage. So the area of the solder joint that is a void versus the total solder joint area. And then we break apart the variables that we're studying on the x-axis. In this case, it's paste area, 60 versus 70%. Then the data sets are also represented as small circles. And then in addition to that, we're running a Tukey-Kramer analysis, which is an honest significant difference test. That Tukey-Kramer analysis is run with a 95% confidence level, meaning we're 95% sure that the data sets are either statistically different or not based on this test. And then that test, we'd like to use the connecting letters report that it spits out. So that connecting letters report is shown at the bottom. The connecting letters report assigns letter codes to each data set. So in this case, the 70% paste area is one variable, and that has a letter code of A assigned to it. And the 60% paste area has a letter code of B assigned to it. Those are different letters. That tells us that those are significantly different from each other, which means that they gave significantly different levels of voiding. So in this particular case, this example, 70% area of coverage actually gave higher voiding overall than 60% area of coverage. The process that we used to do this is shown here. We printed the solder paste, placed components, and reflowed the circuit boards. Then we took pictures of the solder joints, and then we measured voiding. And then we repeated that cycle for 20 boards for each of both stencils. So we made a total of 40 circuit boards and analyzed the data out of that. The data included inspection of wetting or solder fillet formation. We wanted to make sure those perimeter pads were making proper IPC specified solder joints. We also looked at bridging to see if there was any bridging occurring or any skew of the components. And then we measured voiding with our X-ray system. We looked at the area of the voiding and then the size of the largest void. Here are the results. So these are pictures of the solder joints from the QFN10 components. These are organized from left to right. You've got 60% area of coverage with zero toe adder, 70% zero toe adder, 60% area of coverage with 5 toe adder, 70% area of coverage with 5 toe adder, and then down below it's the 60 and 70 with 10 toe adder, and then the 60 and 70 with 20 toe adder. And you can see the solder joints are not really visible with 0 toe adder. 5 toe adder, you start to see a little more flux out there, but still no solder joint on the edge. With 10 and 20, it's pretty obvious that you see solder wetting up the side of the component, or at least beading up around the side. It may not be wetting because that's not technically a wettable surface, but it may be forming a bead outside of that component, which is what it looked like side on view. That was kind of flowing up the side a little bit. These solder joints technically meet IPC criteria, although most people don't want to see big bubbles of solder like on the very lower right, 70% with 20 toe adder. But it's not technically a reject as long as there's no bridging or no skew and spacing isn't violated. And there was no skew observed, no bridging observed on any of the components in any of these circuit boards. So these designs are all technically usable to create good solder joints. Here is the first set of voiding data. This is voiding broken out by stencil thickness. So on the very left, we have overall just all the data lumped together, split apart by stencil thickness. Then in the center, we looked at stencil thickness for the 60% area of coverage, and then stencil thickness for the 70% area of coverage. So on the left, we have 4 versus 5 mils. There's a significant difference in voiding there. The 4 mil thick stencil gave higher voiding overall than the 5. In the center, 60% area of coverage, the same trend is shown. The 4 mil thick stencil gave higher voiding than the 5. And then on the right, 70% area of coverage, the two stencil thicknesses had equivalent levels of voiding. And that's basically due to you have enough coverage with 70% area to minimize the amount of voiding, so the stencil thickness didn't make enough difference there. Generally speaking, increasing either thickness or area of coverage will reduce voiding in the thermal pad solder joint. Here's voiding broken out by area of coverage. So this is separated by the different stencil thicknesses, the 4 mil thick stencil on the left, the 5 mil thick stencil on the right. This is just like a different way to look at that same data set we just talked about. We just sliced it up differently. So if you look at the chart on the left, for the 4 mil thick stencil, 60 versus 70% area of coverage gave statistically similar levels of voiding, no difference. For the 5 mil thick stencil, the 70% area of coverage actually gave higher voiding than the 60% area of coverage. So with a 5 mil thick stencil, you have enough paste there that 60% area of coverage and 70 are going to give you pretty similar levels of voiding. There's not a huge difference here, but they are statistically valid. So here's a breakdown of voiding by component size. We used 3 sizes of QFNs, a 10 millimeter QFN, a 7 millimeter QFN, and a 4 millimeter QFN. And you can see on the left, there are different void levels for each one of these component sizes, and they are significantly different. The small QFN4 gave the highest overall voiding, while the QFN7 gave a moderate level of voiding, and the QFN10 gave the lowest overall level of voiding. And the pictures on the right are perfect examples of that. You've got a QFN10, which has 7% void area in that image, versus 15% void area for the QFN7, and that small QFN4 has 23% void area in that particular image. This is pretty consistent throughout our tests. And this is something we've seen before in prior work. The component size definitely has an impact on voiding. Here's voiding broken out by the toe adder on the stencil. And we also separated this by component. So the QFN4 is on the left, the 7's in the center, the 10's on the right. The toe adder ranges from 0 mils to 5 mils to adding 10 and 20 mils. All 3 of these charts show the same exact trend. Increasing the length of the toe adder dramatically reduces voiding, and that's statistically significant for every one of these components. You can see for 0 toe adder, the voiding level is much higher than for 10 or 20 for every one of these examples. So simply by increasing the length of toe adder, you can reduce your voiding level. So that leads itself to play out our theory that if you put more paste on these perimeter IO pads, the solder paste pulls back into a taller solder joint, and that lifts the component briefly during reflow, allowing gases to escape. And when the component settles back down, that solder joint forms with much less voiding. This is something that we saw from a counterpart of ours. AIM wrote a paper about this, and they had very similar results to this. And we've also seen another company write a paper about this recently, and all three of us agree the results are similar for all three of us. So this one change in your stencil design can have a dramatic impact on voiding for QFNs. Here's some example pictures of voiding by toe adder, and the data broken out a little more refined. We've broken this data out by both stencil thickness and area of coverage and toe adder. So you've got all three stencil designs on this one chart. So you can see we've got 4 mil on the left column, 5 mil thick stencil on the right column, 60% area of coverage at the top, 70% area of coverage at the bottom. And then that's broken out by toe adder from 0 to 20 mils. Again, you got the same trends. From 0 to 5 to 10 to 20, the voiding drops in every one of these. So toe adder changes affect voiding regardless of paste area or stencil thickness. And these pictures on the left are a nice example of that. You've got the QFN7 with plus 5 toe, plus 10 toe, and plus 20 toe from left to right. And you can see how much the voiding dropped from 23% to 15% to 5% just by changing the toe adder on the design. And those are all for the same area of coverage and same stencil thickness. Here's a summary of all the voiding results for all the combinations that we ran. I don't expect you to read this chart. I can barely read this chart, and I'm sitting in front of the computer screen looking directly at it. If you look at the right, what I want to point out are general trends in the data here. So the connecting letters report is ranked from highest void area to lowest void area, and every combination is represented. At the top of this chart, you've got the highest voiding levels were generated by the small QFN sizes, the 4 mil thick stencil, and plus 0 to plus 5 on the toe of the IO pad. At the bottom of the chart, many of these combinations include the larger QFNs, 5 mil thick stencil, and plus 10 to 20 in the toe adder. Those all gave lowest voiding in our study. So here are the conclusions we can draw from this. In conclusion, the linear ramp to spike profile produced the lowest voiding with the solder paste that we chose to use. That may not be true for other solder pastes. So again, I would recommend that you run different profiles with the solder paste you use in order to minimize voiding for that particular product. Increasing the stencil foil thickness from 4 mils to 5 mils had a significant effect at reducing voiding. So if you have the ability to do that, I would recommend it. Increasing area of coverage from 60 to 70% did not have a significant effect in all cases. Sometimes 70% void area gave higher voiding than 60, sometimes 60 gave higher voiding. So it's not a dramatic of enough change to really impact voiding, or at least we saw mixed results. Overall voiding did decrease as the QFN component body size went up. And I know many of you don't have the choice on what type of components you use, but if you do, if you can use larger QFNs, it seems to be helpful. And then overprinting the IO toe on the perimeter pads definitely had an impact. That reduced void area regardless of all the other factors. It overrode all the other factors. So here are recommendations based on these conclusions. We recommend choosing a low voiding solder paste and fine-tune the appropriate refill profile to go with that solder paste. Increasing the stencil thickness or the area of coverage tends to help. Now, I just got done saying that 60 versus 70% area of coverage did not have a dramatic effect in our study. In fact, it gave mixed results. But in prior work, we varied the area of coverage from 50 to 60, 70, and 80% area of coverage. And there's definitely a trend there. 50% area of coverage was too low, and it gave much higher voiding than 80% area of coverage. But with that being said, as you go up to higher areas of coverage, if you go up to 80% area of coverage on a thermal pad, you can have a problem with float or skew of those QFNs, so you got to be careful with that. And then I definitely recommend overprinting to the toe of the QFN IO pads. If you do that, you're going to reduce voiding, and that's going to override some of these other factors. Thank you for your time and your attention for listening to this presentation. If you have any questions, please email us at the email addresses shown here. We'd be happy to talk with you. Thank you. Have a great day.